I'm Nina Snaith. I'm a mathematician. So there are many very practical applications of mathematics to other sciences, to engineering. There's mathematics behind almost anything we refer to as technology. But for many mathematicians, it's not so much these applications that motivate us, but rather a love of the mathematics itself. So what does that mean? Well, symmetry is a characteristic that we humans appear to find very appealing. So both aesthetically, for example, in art, in architecture, in other human beings, but also we find a high degree of symmetry in many objects that are very functional. If you think about your phone, or your umbrella, or your car, or your house. And the same is really true in mathematics. So if you listen to the words that people who like mathematics use to describe it, words like elegant, structure, pattern, completeness, these are manifestations of symmetry. And whereas in the real world, objects can never have exact symmetry, in mathematics, symmetry is perfect. So it's not hard to understand why some people can see mathematics as truly beautiful. But symmetry is also useful in mathematics. So symmetry can give us an idea whether a new theory is complete, and it can point the way to a shortcut to the solution of a problem. In my lecture, I want to illustrate what symmetry is in mathematics and to try and show how symmetry has led to breakthroughs that have revolutionized mathematics over the centuries.
I'm a mathematician, and so I'm here to talk to you about symmetry in mathematics, what it means and why it's useful, and why it deserves to be a big idea in science. So we see symmetry around us almost everywhere. So in nature, lots of things are almost symmetric, but none are really perfectly symmetric. So we see a lot of symmetry in this flower, but you can see the petals are slightly different sizes, they're slightly different shapes. And so the symmetry isn't perfect. As humans, we seem to value symmetry. So we find it attractive. We unconsciously attribute to people who look symmetric valuable characteristics. And so in man-made objects, we find a lot of symmetry. So architects use symmetry to convey some characteristic, like grandeur. But even this object, which looks very symmetric, isn't perfectly symmetric because a millimeter off here and there breaks the symmetry. Architects obviously use asymmetry sometimes to make a point, so they deliberately break symmetry to express some value like energy or innovation. But in mathematics, symmetry is perfect. So these are graphical representations of abstract objects which have absolute perfect symmetry. So they may be shapes or a function, an equation, an array of numbers. But in mathematics, we can have absolute and perfect symmetry. So then the question is, how is symmetry useful in mathematics? So here's a question. So sometimes symmetry can help you solve a question. It can make a hard problem much easier by seeing the symmetry in the problem. So here's a problem. We have a cow who's situated at this point. The cow is tired and wants to go home to the barn at the end of the day, but she's also thirsty. And this here is a river. So the cow wants to go to the river and then to the barn to go home for the night. Right, so she wants to do this. She wants to walk to the river and then go home to the barn. But this cow is lazy, and she wants the shortest possible distance to walk to get a drink and then to go to the barn. So some of you may have seen this problem before. So I want you to take the two sheets of paper, the blue and the yellow one, wave the blue one at me if you know the answer to this already, and the yellow one if you don't know the answer. Okay, so that's good. So most people haven't seen this before. So I want you to take a few minutes and think about this problem. So you're trying to find the shortest way for the cow to go to the river and then to the barn. Feel free to talk to your neighbors to see if you can figure out how you might solve this problem. paper at me if you've solved the problem, yellow if you're still working on it. Okay, we have a few solutions. So for those of you who are yellow, let me give you a hint. So what if the cow was not at this point, but was at this point? Okay, so now the cow is here, she wants a drink, and she wants to get home to the barn. So think about how you'd solve that problem, and then see if that helps you to solve the original problem. So again, talk to your friends and see if you can figure that out. Okay, so now wave at me with the blue card if you've got it now, the yellow card if you need another hint. Okay, so well done, well done. We've got a lot of blue cards now. So of course if the cow is here, she would walk in a straight line to the barn and would get a drink at the river. But now if we compare walking this distance and that distance, we see that the purple bit and the red bit are the same length. So she walks the same distance, and if you chose to move that point, if you dragged it to any other point in the river, you'd easily tell that this distance would be longer to go over here, say, and since this is the same, that would also make the red distance longer. Okay, so you can see by using symmetry, the question which you couldn't solve initially, right, was made quite easy. And that's true in mathematics in general. Often if you spot the symmetry that's at the heart of the mathematical problem, it can make your life a lot easier. So here's another problem. We won't go through this one right here, but I'll leave it as an exercise for you to do if you want. This question is, how do you draw a triangle with the shortest possible perimeter inside this angle here, one corner at the red dot and two corners on the blue lines? And I've drawn the blue lines to look like the river as a sort of hint. So you can think about this. The solution is at the end of these notes, which will be put on the Big Ideas website. So if you want to have a go and then look at the solution, you can do that. Okay, so these were two small examples of where symmetry can help us solve a particular individual problem in mathematics. And this happens in mathematical research. Sometimes you find a solution by using symmetry. But also, even more importantly, symmetry sometimes leads us to the most revolutionary breakthroughs in mathematics. So if we think about imaginary numbers, so let's start with an equation. So we have the equation y equals x squared. So if you plot this, say you choose the value 2 for x, then 2 squared is 4, so we have the point here, 2, 4. That's a point on this curve. And if we choose various other x values, we can plot the curve y equals x squared, which looks like a parabola. So then what if we ask the question, where is the height of this curve? 0, right? So this axis measures the height of the curve, 0 is right here. So where is the height of this blue curve? 0. It's the same as asking when y is equal to 0, which is the same as saying when is x squared equal to 0. So in this picture, obviously the height is 0 when y is 0 and x is 0. So now what if we drew the picture of this curve? So now we've taken y equals x squared and just shifted it all down by 1. So now we have a parabola that sits here. And so now the parabola crosses the x-axis at 2 points. So if we ask the same question, where is the height of the blue curve 0? Or where is y equal to 0, which is equivalent to saying where is x squared minus 1 equal to 0? Then we see the answer is, if you solve it mathematically, you get x is 1 solves this equation, and x is minus 1 solves this equation. If you look at it graphically, you can see that the height is 0 at minus 1, x is minus 1, and at x is 1. Okay, so now let's look at this picture. So now we have y is x squared plus 1, and that's shifted our curve upwards. So now it looks like this. Okay, so we can ask the same question. When is the height of this blue curve 0? Or otherwise, when is x squared plus 1 equal to 0? So a lot of these quadratic equations have two solutions, like we saw in the previous slide, two places where the curve cuts the real axis. And so really by symmetry, what we'd like is for all quadratic equations to have two solutions. But in the 1500s, mathematicians only knew about real numbers. That is the numbers that lie on this number line here. And so they knew that even if you square a negative number, so even if you square, say, minus 1, you get a positive number. And so they couldn't even imagine a number that you would square to get a negative number. So if we rearrange this one, we have x squared is minus 1. And they couldn't even imagine what kind of number would you square to get minus 1. And so they had a problem, right? And they could solve it in one of two ways. They could say, okay, this equation has no solutions, right? Because they knew of no number that solved this equation. Or they could invent new numbers that would give you the desired two solutions to this equation. So if you just do some manipulation with this equation here to solve for x, you get that x is plus or minus the square root of minus 1, whatever that means. So mathematicians were confronted with this. So to see what they did, let's consider this problem here. So we want two numbers that when you add them together give you 10, and when you multiply them together give you 40. Okay, so with our modern mathematics that we know how to solve this. So we can solve y. We can say y is 10 minus x, right, by taking the x over there. So in the second equation we can have x times y, where y is 10 minus x, equals 40. And then we can rearrange the equation. So we have a quadratic in x over here. And by the quadratic equation or whatever, we can solve that to get two solutions, right? X is 5 plus root of minus 15, or x is 5 minus root of minus 15. But in the 1500s, the mathematicians didn't know what to do with roots of negative numbers. But so let's just imagine that we accept that there is something, we'll call it blob, right? So that there is something, which is this red blob, which when you multiply it by itself, when you square it, it gives you minus 15. So we don't know what it is, we don't understand this thing, but let's say there is something which when you square it, when you multiply it by itself, it gives minus 15. Then we can see that it solves this little problem here, because say this solution, let's call this x, let's call this one y. So if we have x plus y, then we have 5 plus blob plus 5 minus blob. Well, the blobs cancel, right? So we get 10. If we multiply these together, multiply this one by this one, you have to do all the cross terms. So you get 25 by multiplying 5 by 5. You get 5 times minus blob. You get 5 times plus blob. Well, they cancel. And then you get blob times minus blob, right? But we've been told that the only thing we need to know is that when we multiply these two blobs together, we get minus 15. So with the extra minus sign there, you get plus 15. You get 25 plus 15 is 40. So in the 1500s, Cardano, a mathematician, realized that if he could just accept that there was a quantity which had these properties, then he could do algebra and he could solve these problems just fine. So and it took another 300 years for complex numbers, for imaginary numbers, to become really sort of well understood and well used. But this was the beginning. So now we know that if we have any quadratic equation like this, we'll always find two solutions if we allow ourselves to use imaginary numbers. You probably met the quadratic formula, which gives you those two solutions. So for example, if we have x squared is minus 1, we solve this and we have x is square root of minus 1, or x is minus the square root of minus 1. So now we have symmetry in the problem. Whatever quadratic we have, it has two solutions. And in the process, we've invented a new kind of number. So obviously, as the years passed, people became more familiar with imaginary numbers. It turns out you only need to invent one new number. That is the square root of minus 1, which we denote as I. Because, of course, the square root of minus 15 can be written as the square root of minus 1 times the square root of 15, or I times 15. And we developed ways to graphically represent imaginary numbers. So imaginary numbers, complex numbers, can have a real bit, an imaginary bit, and we can plot them with a real bit on one axis and the imaginary bit on this axis, so we can kind of visualize a bit better what a complex number is. And now, of course, complex numbers are absolutely essential in modern science. So this is a quantum wave function, picture of a quantum wave function, and you wouldn't have quantum mechanics if you didn't have imaginary numbers. You wouldn't have electrical engineering or digital signal processing, or any of the things that our technology relies on today. So imaginary numbers are absolutely fundamental in mathematics and in other areas of science, and we have them because mathematicians were trying to complete the symmetry, right? To solve the problem, make every quadratic have two solutions. Okay, so now let's talk about another kind of symmetry in mathematics. So now I want you to take your green piece of paper. You should have a big green piece of paper. And I want you to make yourself an equilateral triangle. Okay, and the instructions are on here. Okay, if you get it, you can help your neighbor so that we all have a triangle. Okay, so hold up your triangles. Who has a triangle? It looks good. If you don't, ask your neighbor who has one to help you with it. Okay, so when you have your triangle, put it down on your desk and label the corners 1, 2, and 3. Okay, and then flip it over and label the corners on the other side 4, 5, and 6. It doesn't matter how, just 1, 2, 3 on one side and 4, 5, and 6 on the other. So now you want to imagine that on your desk you have the outline of a triangle like this. And I want you to figure out how many ways can you place the triangle into that outline so that it's in a different position. How many different ways can you put the triangle down in that outline? Okay, so I want you to wave your blue card at me if you think there are more than one way to put the triangle down, and wave your yellow card if you think there's one or fewer ways to put the triangle down. Okay, keep waving blue cards if you think there are more than 2 ways to put the triangle down in different positions. More than 3 ways to put the triangle down in different positions. More than 4 ways. Keep waving the blue card if you think there are more than 4 ways. Yellow card if you don't. Are there more than 5 ways? More than 6 ways? I don't see any cards. Are there more than 6 ways to put the triangle down? Blue if yes, yellow if no. Okay. So a few people think they have more than 6 ways. Are there more than 7 ways? It's it. So let's see. Okay, so I could put my triangle down with the 1 at the top like this. I could put it down with the 2 at the top. I could put it down with the 3 at the top. Or I could turn it over. I have backwards numbers where you have 4, 5, and 6. And I can have backwards 2 at the top, backwards 3 at the top, or backwards 1 at the top. Right? So I think there are 6 different ways, distinct ways, to put the triangle down into that outline. So, but now it's actually more helpful to think of it like this. So let's pick a reference position for our triangle. So I'm going to pick with 1 at the top, like that. And then we think of moving the triangle into each one of those 6 positions. Right? So I could pick it up and put it down as it was. That's an action, which results in it being in its reference position. I could pick it up, I could rotate it clockwise and put it back down. Or, returning to my reference position, I could pick it up, I could rotate it the other way, put it back down. And I'm achieving one of the other 6 positions by doing this. Or I could decide to flip it over. So I could take one corner, and I could flip it, and get one of the 6 positions. Right? And then returning to my reference position, again, I could flip by any one of the corners. Okay, so now instead of thinking of the position of the triangle, we're thinking of doing an action to take the triangle from its reference position into one of those 6 positions. And the benefit of doing this, of thinking of it as an action instead of just a position, is that we've introduced time. So now we can think of making a sequence of moves, one after the other, in order to the triangle. So I want you to think about a series of questions. So what happens when you perform two of these moves in sequence? So maybe I take my triangle from the reference position, I do one move, and then without returning it to the reference position, I do another move. Maybe I rotate it again. Okay? Or maybe I start from this position and I decide first I'm going to flip it, and then I'm going to rotate it anti-clockwise. Okay, so I want you to take your triangle and see what you can do by doing two moves in sequence. So without returning it to the reference position, you do one move, a flip or a rotation, and then you do another one. And so the questions you can think about are, when you perform two moves, one after the other, is there any way to make the result different from one of the original single moves? If you've thought about that one, you can move on to some of the other questions. So take your triangle and have a think about those questions. Okay, so what do we think? What about the first question? So the blue card is an answer of yes, the yellow card is an answer of no. When you perform two moves in sequence, do you always get back to one of your original 6 positions? So blue if yes, yellow if no. Okay, so a lot of blues, so that's good. So you've just discovered group theory. So this is an area of mathematics it can be an abstract area of mathematics, but we're going to use the rotations of this triangle to figure out some of its properties. So what about the second question? So if you do two moves, but you do them in one order, 1, 2, and then you do them in another order, do you always get the same result? So blue cards if it's yes, and yellow card if it's no. Okay, so I'm seeing some yellow cards. Well, let's work this out. So let's make ourselves a table. So you guys have to help me with this. So we have a table, and first we're going to do a move down here, and then we're going to list it up here. So I is like the identity. It means we don't do anything, right? It's the move where we pick a triangle up and we put it down exactly where it was. C is rotate clockwise. A is rotate anti-clockwise. T is flip around the top corner. So if the triangle is there, flip around the top corner. R is flip around the right corner. L is flip around the left corner. Okay, so I want to fill out this table, and we want to know what's the result of doing first this one and then this one, right? It's equivalent to doing one single move, and what is that single move that it's equivalent to? So you guys have to help me. So if I do first the identity, which is do nothing, and then the identity, which is do nothing, what do I get? Okay. So what if I do the identity and then I do a clockwise rotation? What do I get? Yeah. If I do the identity and then I do anti-clockwise rotation, if I do the identity and then I do a flip on the top, I get, yeah. If I do the identity and then a flip at the right corner, yeah. And then if I do the identity and then a flip on the left corner, I get the left. Okay, so now let's do the second row. You might have to get your triangles out to do this. So what if I first do a clockwise rotation and then I do nothing? Let's just see. What if I do a clockwise rotation and then a clockwise rotation? What's that equivalent to doing? Yeah. And if I do a clockwise rotation, then I do an anti-clockwise rotation, then I've just done nothing. What if I do a clockwise rotation and then a flip around the top? What do I get in this box?
Right corner R.
I get an R? Does everyone agree that I get an R? Okay, what if I do the clockwise rotation and then a flip on the right corner? I pick up the right corner and flip it. And then if I do a clockwise rotation and then flip at the left corner? Is that right? Something's wrong here. Okay, if I do a clockwise rotation and then I flip on the right corner, that is the same as doing No, what have I done? Okay, I'm doing a clockwise rotation, and then I'm doing a flip on the right corner. Okay, so that's the same as doing a flip on the left corner. Is that right? And if I do clockwise rotation and a flip on the left corner, it's the same as doing, okay. All right, so now about the next line. If I do an anti-clockwise rotation and then I do nothing, I get anti-clockwise. If I do anti-clockwise rotation and then clockwise, I get back to identity. Anti-clockwise, anti-clockwise. Anti-clockwise, anti-clockwise? Yeah, it's the same as doing one the other way. Okay, now here are the trickier ones. So again, you have to help me. If I do anti-clockwise and then I do a flip at the top, what do I get? L. Anti-clockwise and a flip on the right corner. Anti-clockwise and a flip on the left corner. Okay, if I do a flip on the top corner and then identity, that's just T. If I do a flip on the top corner and then C, clockwise. People are saying R. Does everyone agree? Yeah. If I do a flip at the top corner and then anti-clockwise. If I do a flip at the top corner and a flip at the top corner. Flip at the top corner and then a right corner flip. Is C, does people agree with C? And flip at the top corner, left corner, hopefully is A. So if I do a flip on the right corner and then identity, that's R. If I do a flip on the right corner and then a clockwise rotation, flip at the right corner and then anti-clockwise, should be T. Flip at the right corner and then flip at the top corner. Flip at the right corner and then flip at the right corner. Should be I. Flip at the right corner and flip at the left corner. There's something wrong with that. So can we check this one? If we do the right corner and then the top corner? Can someone do it for me? Okay, so if we think this one's A, and this one's C, let's see what we get in the last line. So what if we do left and then identity, that's left. If we do left corner and then counter and then clockwise, what do we get? Someone says R. Can we check that? So flip at the left corner and then clockwise. Someone says T. That sounds like it could be right. Left corner and then anti-clockwise. Left corner and then flip at the top. If we flip at the left corner and then we flip at the top. Do we all agree on A? So we have an error somewhere else. Is this one A? Okay, well something's wrong here. Let's do this one. So if we do the left corner and then the right corner, what do we get? Wait. If we do the left corner and the right corner, what do we get? What do you think? Try it with your triangle. Okay, we flip at the left corner, then we flip at the right corner. That's like okay, so there's a problem somewhere. Can we check this line here, the line with the right corner? So if we do a right corner flip, and then we do a top flip, then this one is C according to me, this one here. You guys want to confirm that? And that hopefully means that this one is. So that means this one has to be different. So okay, we do a right corner. And then we do a left corner.
When you do a top flip and then a right flip, is it meant to be anti-clockwise instead of clockwise? And when you do a top and a left, it's not clockwise instead of anti-clockwise.
What do we think? Those two? Okay, is everyone, were we happy with that? Thank you. that at least looks right. Okay, all right, so let's assume that we've got that right now. So what have we discovered? Well, so first of all, we have indeed confirmed that if you perform 2 moves one after another, then you get back to one of the original 6 moves, right? You can see that we managed eventually to fill out this table. Is the result the same if you do 2 moves in one order or in the reverse order? So say we do, I don't know, we do a T and then a C, or if we do a C and then a T. So those are the same. If we do, let's try and find one that's different. If we do a T and then an R versus an R and then a T. Okay, so here, if we do T then R or R then T, then we get different answers, right? So doing the moves in different orders sometimes gives us different answers. So it's not like multiplying numbers where you can multiply them in any order. The order matters. And this is important in areas like quantum mechanics. The uncertainty principle is due to this issue that you can't always multiply 2 objects in the same order and get the same thing. So what about the last question? Can you find any number of moves smaller than 6, so smaller than the full set, that always gives you something back within that full set? So can you look at this picture and see if that happens? Yeah, exactly. So if we take this top corner, then we can see that if you perform in any order 2 operations, I, C, or A, and then a second one, you always get back I, C, or A. You never get into the region where you have a transformation from a flip, so that the rotations form a little group on their own. That you always get back elements from that same group. Okay, so like I say, we've discovered group theory, which means that when we perform these operations, you can perform any number of them, and you'd get back something that's equivalent to one of the original operations. We have an operation which does nothing, and we have operations which sort of restore you back to where you were. Like if you do a C and then an A, then you get back to the original position. Okay, so we've learned that symmetry, we've learned what symmetry means in mathematics, and that symmetry can be useful, right? Not only for solving individual problems, but also for it leads to some of the biggest breakthroughs in mathematics have come about because mathematicians are looking for the symmetry in the problem and trying to complete the symmetry in the problem. So that's all for symmetry in mathematics. Next week you'll hear from Mark about symmetry in physics. Yes, so thank you very much.